go again. All right, so remember to get the handout set from the module so that you have it before we start, okay? So that you can see what I'm saying, because it's definitely harder to explain things. And some things are covered here so that it's easier for me to not have to write it all up in the board, all right? So you will notice that the first part says metric prefixes. So we mainly deal in the metric system. And so some of them are bolded because those are the ones we use by far the most. And so those are the ones that I think it behooves you to memorize. The others get used less. Maybe deci shows up, okay? So you're looking at kilo, centi, milli, nano. Angstrom will show up, but it will be part of experiment 11 in lab, and it's up to the instructor. There are things that get measured in angstroms like bond lengths and things like that. Okay, an angstrom is 10 to the minus 10 meters. So remember that these are attached then to a unit of some sort. Here I have a gram, so there are these equivalencies that are important to remember. So if we're saying that centi, milli, nano, and kilo are the ones that matter, then if you have 1 gram, that's the same as 100 centigrams. You have 1 gram, that's the same as 1,000 milligrams. You have 1 gram, that's the same as 1 times 10 to the 9 nanograms. You have 1 gram, that's the same as 1 times 10 to the minus 3 kilograms. And so you have to feel very confident switching back and forth between these. And we'll practice a little and I'll show you how to use these equivalencies, okay? Then we have something here on basic units to remind you. Typically we deal in volume of liters, but be aware that we could also be doing some meters cubed, as well as milliliters, as well as centimeters cubed, right? And so you've got to be able to convert between these. But again, most of the time we'll stick to liters and milliliters. Any distance is in meters, but we could have centimeters, we could have millimeters. Mass is typically in grams, but we could have kilograms, occasionally milligrams in the lab. But again, you know how to convert. And then temperature is going to be in Celsius or Kelvin. We don't use Fahrenheit. Time is typically in seconds, although you'll find the random problem that it's in minutes or hours. And so you have to know the conversion between seconds and minutes and hours. Again, this is something you would know, right? That one we expect you to know. Now, pressure will not be discussed here. We leave it for when we cover gases so that we don't overwhelm you with too much. But if at some point you need me to do a whole presentation on pressure, which is a concept that a lot of students have a hard time with, you need to tell me, okay? All right, so there are conversion factors here. I didn't mention that there. And I put many of the ones that you probably know, obviously like 12 inches is a foot and all that. We tend to stay away from the English system, but just in case stuff is there for the English system, one that does really matter, and it should have been capped, it should be ML capped for the L. I'm sorry, it's not that way. Is 1 millimeter is 1 centimeter cubed. That will be really important as we convert from densities to volumes a lot. And so I just want to remind you, that one's bolded to remind you of that, okay? All right, so then the next page has something about equations. And I put that there not so much because we're going to be doing all of these things, but rather because as a person who's at the interface of chemistry and physics, I find that having it all summarized in one page when it comes to force and energy and pressure makes it easier for me to remember the units. At the bottom here, if you know your units for energy, for example, they're in joule or ergs, depending on whether you're in MKS or CGS. I don't memorize the conversion factors. A lot of people do. If I know what a joule is, I know how to change everything to the new unit and do dimensional analysis to figure out the conversion factor. Because if not, it's just too many conversion factors I have to remember, okay? And so, again, this is here to help you visualize how the two systems are and all that, and it might be very helpful for you in physics to have that, okay? And we'll leave it there because the rest I think is on graphing, and so I'll get to the graphs in part 2. Okay, so dimensional analysis. So this is a skill that you don't have to have, but it will save you massive amounts of time in physics, engineering, and chemistry courses, all right? Dimensional analysis is the use of units that allows you to solve problems, often bypassing having to know the equation. So depending on how your high school physics, high school chemistry courses went, you were sitting there memorizing equation after equation. That works, right? But sometimes by just following the units, you are able to do the problem without ever having to remember the equation. And so, again, there have been some students that have learned this from us in Chem 1A and then come back and said, you made my physics and engineering courses a lot easier than a lot of people because I figured out how to master dimensional analysis. So I'm going to give you a couple of examples here, and we're going to keep working on it a little bit. It's going to pop up a lot when we do stoichiometry, how to convert things from units of moles of water to moles of carbon dioxide because you have a balanced reaction. So it's a continuous thing that we will use in a lot of problems in chemistry. So say, for example, and I'm taking a very simple example here, a jogger is running at a pace of 110 minutes every 45 seconds. What is the jogger's speed? So you're going to sit there and you're going to look for the equation for speed or velocity. They're interchangeable. Velocity tells you the direction. Speed just gives you the magnitude of the velocity, okay? So we're not worried in which direction the jogger is going at this moment in time. We just want to know how fast. And so a lot of people approach this by going, okay, so what is the equation for speed, and setting it up. I just look at the units. I've got meters, there's my meters. I've got seconds, there's my seconds. So I have to take the meters and divide them by the seconds. And so I don't have to waste any time thinking about what is the equation for this. So I'm going, I have to have units of meters over second. So I'm going to take 110 meters divided by 45 seconds. And so the average speed of the jogger is 110 divided by 45, which is 2.4. All right, so let's look at this. I have 2 digits here, so I have 2 sig figs. This could have 2 or 3, but in the absence of being told what's this in scientific notation, I have to assume the worst case scenario. So I'm going to assume it's 2. Then I'm looking at this being a division, and when you multiply and divide, the number of significant digits is the number of the guy with the least. So this is 2 and 2, so that's why I only get 2 here, and the units are meters per second. And so what you're seeing now is as I start doing more problems, I will be bringing up significant figures. So we keep going over this over and over. All right, then there's the question here of convert this to millimeters per hour, okay? And so this is, I'm starting with, I know where I'm starting with 2.4, or you can start with these two, either way works, meters per second, right? And when I'm done over here, I have to end in millimeters per hour. All right, and this is again dimensional analysis. Now I have to start thinking of something called equivalencies. I've got to figure out how do I change meters to millimeters, and how do I change seconds to hours, okay? So if I'm looking at this, I need what I'm going to call equivalencies. So I know already in milli and 1 unit, so I know that 1 meter is equal to 1,000 millimeters, right? So that one's there, easy. And this equivalency, it means they're the same thing. So if I use this in some way where one is written over the other, they're the same thing. So it's like multiplying by 1, all right? And then I know that 1 hour has 60 minutes, And I know that 1 minute has 60 seconds, okay? And so those are all the equivalencies that would allow me to convert meters to millimeters and seconds to hours. So now I have to think about how I'm using this. And so I'm going to start with the easier one of the two, which is the one-stepper, right? So I want to get rid of the unit of meter. So my meter goes in the bottom. And I want to bring in the unit of millimeter. And so I'm going, is there a relationship between these two that makes them equal? So literally, I'm just multiplying this by 1. And the answer is yes, it's there. So in front of the meter, there's a 1. In front of the millimeter, there's 1,000. And that will cancel out those units, right? And so I've got it in millimeters. The next one I got to do is I've got to go from seconds to hours, but at least right now, and again, some of us will do this quicker. We know there's 3,600 seconds in an hour, but if you have to go by step, then by step is fine, all right? So I know I have to get rid of the unit of second, and the relationship I have that second there says minute, right? So I have 1 minute, 60 seconds, right? And that's a definition, that's an exact number. So these are exact numbers, right? Milli is the definition of 1/1000th of a meter. By the definition, a minute has 60 seconds, and it's 60.000. So all these two numbers also have infinite number of significant digits because they're exact. So now I got rid of the second, right? But I still have minutes, and I need hours. So I'm looking at this in the setup. The minutes on the bottom there, so I want the minute on top, and the hour is what I'm going to get in the bottom. And so I have 1 hour, 60 minutes, okay? And so when we clean this up, I notice that the units cancel out, so my minute cancels out with my minute there. And so I've got it all converted to the correct units. So I have 2.4 times 1,000 times 60 times 60. And so I have 8.64 times the power of 10. So I have 2 digits, infinite, infinite, infinite. So my answer gets 2 digits. So I have 8.6 times 10 to the 1, 2, 3, 4, 5, 6. 6 millimeters per hour. And so notice that the other mental check I can do here, I can think about this, okay? I can go, hey, if he was traveling 110 meters in 45 seconds, meters are much, much bigger than millimeters. So if I reduce it to millimeters, it's going to be a big number. And in addition, if I add more time that he can travel longer, it's going to be a big number. So I'm not surprised that I got a really big number here, right? If I had set this up wrong and gotten something like 10 to the minus 6, I can then do a common sense check and go, whoa, 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 whoa. Just because I got an answer doesn't mean I set this up right. I expected to get a big number here because I was looking at the distance traveled in a longer amount of time and in a smaller measurement of millimeters. So I was expecting a big number. If I don't get a big number, I can go, wait, I put this in the calculator wrong, or I set this up wrong. I set this up incorrectly, okay? And so those are common sense checks that have to be done. And what you're doing here is dimensional analysis, and at no point was there any equation brought up or memorized, okay? Also, remember, we have these equivalencies, so let's talk about that a little bit, because you have to be able to create equivalencies that are correct. A lot of people then start doing equivalencies and come up with equivalencies that are not true, so they don't work. All right, I'm going to switch to another board, so give me a second. This here. Sorry. Okay. Here's the next one. My calculator, so here we go, okay? So these equivalencies, right? So for example, you could say a meter is 100 centimeters, that's the definition, but it's also 1,000 millimeters, and it's also 0.001 kilometers. And so any of these two any one divided by the other is the same as one. And so you can interconvert at any time between one unit set and the other. We can even have chemical equivalencies. And so I want to bring that up now because I want you to be able to realize that we will use this. So if you're talking about a molecule of water, not a molecule of something else, right? It has to be a molecule of water. Then one molecule of water is the same as 2 atoms of H. Clearly a molecule of CH4 would be equal to 4 atoms of H. So these equivalencies, when applied to a compound or in a balanced reaction, allow you to substitute for one species for another. And so we'll be doing this a lot in chemistry. All right. The equivalencies also allow you to convert units for systems for which you don't have a conversion factor memorized, right? And this is really interesting. So if I tell you 1 meter square and I ask you to fill in the box for 1 centimeter squared, you need to fill in that number. So if you want, turn off the computer, turn off the video and do that and decide what you get. Okay, so turn it off now. Okay. Now, you're coming back after trying the problem yourself. Here's the deal. When we do this in lecture, okay, 70% of the students get it wrong. And then we put it in another quiz, and 60% of the students get it wrong. And then we put it in the first lecture exam, and 50% of the students get it wrong. And then we put it again, because we keep doing this over and over to see if you put in the time to learn how to square and cube units. And we will find that we'll have 40% of the students still getting it wrong in the final. Then we go to Chem 1B and I put it again in a Chem 1B test and I'm back to like 50% of the students getting it wrong because they've elected to forget how to do this, all right? You cannot forget how to do this. How to square and cube units is extremely important in engineering, physics, and chemistry, all right? And so you can't make up equivalencies. So for me to write the number there, I know the answer quickly, but it's because I did the calculation in my head. This is not 100. I agree that 1 meter is 100 centimeters, but 1 meter squared is not, I repeat, is not 100 centimeters squared, okay? And if it helps you, build the box, okay? So remember, distance squared is a unit of area, right? So if you make this 1 meter and this 1 meter, this guy is, 1 meter squared. It's a meter times a meter. But remember, this is 100 centimeters and this is 100 centimeters. So when you multiply 100 by 100, you don't get 100, right? And so either you're stuck building the box if you need to see that, or you can do the following. You go 1 meter squared, right? And you're trying to change it to centimeters squared. And so then you need to look for the equivalency, the thing that equals 1 that would allow you to do that conversion. So you have meters there, right? And you have centimeters on top. So that will cancel the units, but they are squared. So you've got to square the whole thing. Now the relationship is 1 meter, 100 centimeters. So again, I agree that's correct, but it's the whole thing squared. So you have to square the 100. So this is then 1, 2, 3, 4, okay? A lot of students cannot do this and continue having issues doing this over and over and over in Chem 1A, Chem 1B. Actually, I once talked to a person who hires civil engineers, and he says all civil engineers he has hired know how to do all the calculations required for civil engineering, He just knows they're going to be wrong with the units because they don't know how to convert units. An inability to keep track of units or understand units has caused some very dangerous things. In a case in Japan, someone mistook an amount of grams for kilograms and nearly got to critical mass on uranium, which would have caused a major disaster in that uranium purifying facility. Not keeping track of whether you're in English or the metric system, there was, and I can't remember which one it was, a Land Rover of some sort, sent to either the moon or Mars or whatever, I want to say back in the 90s, where it was sent up, I think, by the Jet Propulsion Lab in over in Southern California, but being managed by the NASA lab in Arizona or something like that. And one was talking in metric and one was talking in English units, and they got some things wrong. And I think they caused some significant damage. So just because you know the equations and you plug and chug, if you don't keep track of the units and make sure that the units cancel out and come out as needed, the problem is worthless, all right? You're stuck building things incorrectly, okay? Or doing things incorrectly and possibly having some issues. All right, so we have kilometers cubed and meters cubed. When you cube a distance, you have a volume. So as I mentioned before, volumes, we often do liters, milliliters, but we could also have meters cubed or centimeters cubed. And I will point out there is one very important bolded conversion that will often come up. It's 1 ml is equal to 1 centimeter cubed. That will often be helpful. It will be helpful in this next problem. Okay, so you have 1 kilometer cubed to meters cubed. So again, you're starting out with 1 kilometer cubed, and you're trying to change this into meters cubed, right? So you know that you want kilometer on the bottom because that's the way the kilometer is going to cancel, and you want meter on top, and you know the conversion. You do either way. You can put 1,000 meters is a kilometer, or you could put 1 meter is 0.001 kilometers, your choice, but the unit has to be cubed, right? So that the cube out, that means the 1,000 gets cubed, and so your answer is 1,000 times 1,000 times 1,000, so 10 to the 3 times 10 to the 3 times 10 to the 3, so this is 10 to the 9, okay? And we might use that conversion factor or some of these later in another problem. All right, so let's practice a little here. So you have a density in grams per ml. So I have 1.00 grams per ml. And down here, I don't know how many steps, someone wants that in kilograms per meters cubed. All right? And so the quick one I know, right, I'm going to put a little thing here so I have some more space. The quick one I know is, 1,000 grams is 1 kilogram. That's the definition of kilo. It's 1,000 of them, okay? So that one's easy, right? And then I see ml to meters cubed, and I agree that they are all, volumes, but this one makes me think I'm going to need that thing there. So I have it there, right? And then my centimeters cubed, I'm going to have to change to meters cubed, but I know how to do that, right? I already know how to change those cubes quickly, right? So here we go. So this guy's here. I'm going to take care of the kilogram quickly. So gram on the bottom, kilogram on top. It's that one. So there's 1 there and 1,000 there, right? And then I want to change that ml to centimeters. So ml is on top, centimeter cubed is on the bottom. So it's a 1-to-1. And then I know how to do centimeters to meters. So centimeter on top, meter on the bottom. 1 meter is 1,000 centimeters, but the unit is cubed. And so that's what I have to do here. So I have 1, and this is actually very straightforward because that's a 1. So this is 10 to the 3 here, and this is 10 to the 6. So I'm going to end up with 10 to the 3, but you can try it out. Divide by 1,000 times 100 cubed equals 1,000, right? And so then I have to decide how to write that 1,000. So my answer is 1,000. But that might not be my final answer because this has 3 sig figs, right? And this is infinite because it's a definition, and this is infinite because it's a definition, and this is an infinite because it's a definition. And so I got here, remember this is still the same unit system. Liters are still metric, okay? So that's a definition. Had I gone to gallons here, then that would have some conversion factor. So this has 3 sig figs. So I want the answer to have 3 sig figs. So I would have to write 1.00 times 10 to the 3 kilogram per meter cubed. Okay? Does that make sense? All right. And again, I made that unit bigger and I made that unit bigger. So I'm not sort of surprised here maybe that I have, you know, when I'm looking at a larger volume of this, and in kilograms, I've got a somewhat higher density in terms of a number. These are still the same thing, just different unit sets. By the way, 1.0 grams per ml is roughly, or it's the density of water, to 3 sig figs. If you want it to 4 sig figs, which is part of experiment 1, you're going to measure it. You're going to use a pipette, which is going to be good to 4 sig figs. You're going to use an analytical balance, which will give you as many as 4 or 5 sig figs. So you'll be able to find the density to 4 sig figs. So it's going to be typically, it is slightly less than 1.00. It's 0.99 something, right? But if you round it to 3 sig figs, then we often use 1.0 or 1.00 for the density of water. All right, so that's one problem. We've got one more problem to practice with. Sorry, let me get my calculator and let me move over. I gotta go all the way around. You can look at the problem and start reading it while I go get the markers that I left away. Okay, so got a problem here. Let's visualize it a little bit. So an oil tanker spills 1 times 10 to the 4 liters of oil in the ocean. That is nothing compared to what an oil tanker often spills when it breaks open, like the Valdez did in Alaska a long time ago, but we picked a number. The oil forms a layer that is 3.0 times 10 to the 2 nanometers thick. Remember, oil floats on water, okay? And so they don't mix, or they don't mix. And this has to do with intermolecular forces, which is experiment 11. When that layer forms, it then spreads out over a significant amount of the ocean, okay? And so the question is, what area of the ocean in meters squared is covered by that thin layer of oil? So you know that the layer looks like this, right? And this is 3.0 times 10 to the 2 nanometers, right? And you know that this is a volume. And so you have a volume, and this is a height. Then what's left is area. So your problem is to find the area. So it's not really mathematically a hard problem. So you have volume equals area times height or length, your choice. So mathematically, if you don't give a damn about the units, it's very straightforward. The problem is that you've got to convert the liters to meters cubed, right? Because your final unit is meters squared. And you've got to convert the nanometers to meters so that the units all work out, okay? So how you do this, whether you do this in one step, multiple steps, substituting in the equation, it's going to depend on each one of you. you have noticed that I often set it up as just one long calculation. Other people have to do all the conversions first and then plug a chunk into an equation. There are many ways of doing these problems. Some are more efficient in terms of they take less paper, or they take less writing, and others are not as efficient but still okay. So I mention this because in a test, you have a question for a test, right? Here's question 1. And someone's going to leave a lot of area if it's a test you're doing by hand, not unfortunately a Canvas test. If I set up the calculation in a straight line, here's question 2, I might use very little of that space. If on the other hand I do multiple steps, then I use all that space. Unfortunately, some of the people who sometimes do it in one straight line then freak out because they go, that was too easy. Why did they give me so much space? And then they tend to erase what they did and then come up with something more convoluted based on the fact that they see a lot of space and question then what they have done, okay? All right, so for sure, I want to change those liters to meters squared first, because that's the units that's, at least in my case, is upsetting me more, right? I'm good with meters squares and nanometers. I know those conversion factors, right? So I have 1.00 times 10 to the 4 liters, right? And so I'm sitting here and going, okay, I remember that 1 liter is 1,000 milliliters, because that's the definition of milli. And then I have that conversion factor, the 1 ml equals 1 cm cubed. And so those two will get me so that meters start showing up for this liter, which is how I get the units to start at least being all in some meter, right? Whether nanometers or whatever. All right, so I'll go liter here and ml here, so that's 1,001, right? And then that got rid of the unit of liter. And then I get 1 cm cubed is 1 ml. And so then I got rid of the unit of ml. And then if I want this in meters, so I can save a little time here, I have 1 meter on top and 100 centimeters on the bottom, because that's the only way I'm going to get rid of the centimeters, but I have to cube it, right? So I have to cube it. Okay. So again, these are powers of 10, so you can do it quickly in your head if you know how to do that, like I do, but let's plug it in. So 1 times 10 to the 4 times 1,000 divided by 100 3 times. So divided by by a million, right? Got 10, all right? So let's do this again, just to make sure. I have 10 to the 4, plus 3 is 10 to the 7. 10 to the 7 divided by 10 to the 6 gives me 10. So I have 10, and then I have 3 sig figs, infinite, 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 so 10.0 meters cubed. And you can check my math. I did it in my head, and I did it here, and I think I'm still good. 10 to the 4 plus 10 to the 3 is 10 to the 7, divided by 10 to the 6 is 10 to the 1. Okay. All right, so I have that volume. So this is volume. Right? So I got that guy now in meters squared, or in meters cubed, excuse me. Now I've got the height is in nanometers. So again, we can work it out here. 3.0 times 10 to the 2 nanometers, right? 1, I shouldn't do 1 at the bottom because I got to do the conversion first. I need nanometer here, I need meter here. If you recall, nano is 10 to the 9, so I have 1 meter is 10 to the 9 nanometers. So this is going to give me 10 to the 2 divided by 10 to the 9. So I have 3.0 times 10 to the minus 7 meters. That's the height. So that's h, all right? And again, I have to write this out because I'm teaching it to you, so I want to see all the steps. but I might do that conversion in my head, okay? Sometimes I do these quickly and then I'm not worrying about them so much. All right, so if you just want to use the equation there, volume equals 10.0 meters cubed. And then I have A is what I'm looking for, the area, right? And then I have 3.0 times 10 to the minus 7 meters for the height. And so I have 10 divided by 3 exponent 7 negative. So I have 3 sig figs, 2 sig figs, so my answer only gets 2 sig figs. So it's 3.3 times 10 to the 1, 2, 3, 4, 5, 6, 7 meters squared is the area covered by the oil. Okay? Any questions or issues, then come back and review, check your equivalencies. Again, the nanometer one, I got it from before. We had the gram and the nanogram, so that's a quick conversion there. And so all of these types of problems, again, we've done them all in one step, but here's the liters converted to meters cubed. Here's the nanometers converted to meters, and then I can use the equation. It could have been done in one ugly full step and taken up less space. And it's a choice again. How much detail you need to explain how you do a problem is a decision you have to make. Okay, it's whatever helps you understand the problem better. All right, we're going to leave it there. I have to come for part 2 for graphing. Okay, thank you.